I'll start recording. Okay. So we got a question here. Remember, if you want me to go over something, just when just email me during the week. And okay. So what we have here is a transistor circuit that is being used as an amplifier, right? And sometimes it can help to identify what's going on, right, before you begin. And this bit here, right, that would be a common source amplifier, this being the drain. Is it so big? Okay. That's the drain, that's the source, and that's the gate. All right. Now, interestingly, right, this is the output and it's going into the source of this transistor. And so guessing, right, that's going to be some kind of common gate, right? And again, like intuitively, V out over Vx is going to be inverting, right? And if I recall off the top of my head, common gates don't invert. And so it would be non-inverting. So inverting times non-inverting would be, I should get some kind of minus sign there. All right. Now, for those of you who haven't had 122, right, let's just do a quick kind of overview. All right. When we do our op-amp circuits, they're internally biased. And so they kind of work at DC or AC, and you can just, analyze the circuit almost as is, right? And if you wanted to look at high frequency effects, right, you just kind of put something in the transfer function for the op amp. But for these transistor-like circuits, there's really two steps. There's a DC analysis, and then there's like an AC analysis. And the DC analysis is going to give you things like transconductance, and output resistance. All right. The thing is that we have an equation here, right? ID equals Kn divided by 2 VGS minus VT squared. which assumes you're in saturation, which means your VGS is greater than VT. All right. And yeah, I'm forgetting a little bit. All right, this is a MOSFET, and it's got more than one current voltage relationship depending on what the relationship is between the drain gains and sources, right? But really, the gate is really just like a channel control device, and you're controlling current between the drain and the source, right? And it's clearly nonlinear here in terms of VGS. But there's some things, like there'd be this slight slope to this line, and the flatter that line, the larger the resistance, all right? And the larger that resistance, the more ideal it will be. And a lot of times you assume that it's ideal to get some quick answers, all right? So, you know, where V equals IR for a resistor, or V equals what? ZC, IC, or ZL, IL, right? Those are all these linear terms that you're familiar with. These terms, right, transconductance and resistance here, they all change depending on where you are on that curve, okay? And so you need to do two things. Find out where you are on that curve. That's the DC analysis, right? And then convert it to an AC circuit to do the AC analysis, right? Now, again, this is just for those that haven't had it yet. Okay, it's just not meant to be a complete lesson here, but how things work. And yeah, you really kind of need your nodal analysis and things like that we didn't really use in 110. But you actually did in 98, of course. So we have a current going here, and this is drain. And we know that the drain current, or drain to source, right, that has a relationship. And the thing is just so you know, in modern devices, sometimes that's not 2, and sometimes it's modified to give it a little bit of a slope. And there's a lot going on in this term with from 98 mobilities and oxide thicknesses, velocity saturation, a lot of effects. All right. And so it really matters what this is, because that will determine what your small signal parameters are. So that's the equation for the transistor. And you just assume saturation, right? Then might not look like it, but there's a loop here, right? So you have VDD, or minus VDD, plus IDRD, plus VDS, okay? And so this is known, and we don't know that, and we don't know this yet. Okay, I'm gonna just change colors here. But what do we know? Well, we know VGS here, right? Because this is the input. So if we assume we're in saturation, which means VGS minus VT is greater than VDS, then this equation will be true, right? And you can check to see if that's true. So we know this and we know that, all right? So now what you can do is solve for RD to make sure that VDS is right. Or if you assume an RD, then you can check if that is right, all right? But once you have that current, right, and you have that VGS and you have that VDS, you can get these small signal parameters, which I'll talk about in a second, GM and RO, and there's a, which is kind of equivalent to lambda as well. All right. So I'm not going to go through an example here, but you would be given these parameters like what's VT, KN, things like that. And then you would just either design RD, or if RD is given, right, you just make sure that VDS is right. So so that would be the DC part, all right, is finding these values, right? And then we go into the AC part. And just as a quick kind of example, right, that I might have talked about last time, is that this is a nonlinear curve, right? But if I pick a point, a bias point, and I only let it modify a little bit, well, if I'm just trying to say that I'm zooming in here, right, it'll look like a straight line, right? And I have a I, so if this is I and this is V, right, and I have a delta I and a delta V, well, 1 over that would be an equivalent resistance for that diode. Now, if I biased over here, it would be different. If I biased over here, that RD would be different. So this is the same thing that we're doing here, except there's a transconductance, right? A current to voltage, you apply a voltage and you're going to get a current, right? And it's a way of translating that. And then this output resistance is kind of like what I just said over here. Okay, so you find this bias point and you assume you don't move much about it. So let's come back here. And now it's kind of like you take the derivative of everything. Okay, well, V in is going to be AC, so it won't be 0. And V out shouldn't be 0 either, right? Ground is certainly going to stay ground. But now here's something interesting. If that's a 5-volt power supply and it's constant, right? And I take the derivative of it, right? It's going to go to 0. So I'm just going to draw this resistor and one end is tied to 0. And here's my V out. Now, what do we do with this transistor, right? And there's all these nonlinear equations, but now we're at one point and we're taking the derivative of it, right? And so remember I said, if I change this, I'm changing the current, right? So it's a voltage controlled current source. So I draw the current source, right? And VGS or VN, right? Because it's VN to ground and S to ground, and S and ground are actually at the same thing. So I can replace that. This is the drain, and the way you draw these is that would be the drain, that would be the source. And as drawn, ideally, there's no connection here, right? But there's actually feedback capacitances and even resistances. So what is this current? Well, it's VGS GM, right? The GM converts a voltage to a current, and you're getting this from your DC. Now, this might look a little hard, so you redraw it. Okay. And really, what's V out versus V in at this point? Well, it's probably one, the hardest thing to get around your head around is that current source forces a current, right? Through this loop. And you have plus and you have minus, right? But VRD, right, defined by plus to minus is equal to minus VD. Okay, so VD, right? If I put my voltage source, my voltmeter, I put my positive here and my negative here, right? And I'm measuring that node voltage with respect to ground, right? So whenever you see V out, it's V out to ground, right? Or VD to ground or VS to ground, right? But this is a device voltage, right? Like this, and it's opposite, right? Which, I think causes some trouble, right? So what is VD, right? Well, it's minus VRD, which equals minus, well, what's the current? VGS, GM, RD, and we solve for VD, which is V out. And it should be called VDS, actually. VDS divided by VGS is minus GM RD. Okay. So that would be, in the most simple thing possible. Now you can add transistors and resistors and current sources and all kinds of things. All right. And this assumed that the output resistance across this current source, it was ideal, so it was infinite. But a real transistor will have some finite resistance. Okay. So that's like the common source amplifier. Now, sure, you can put resistors here. I can then short the resistor, and there's a whole lot of other things to it. Where does this VN come from? Well, you actually have to bias it, right? So now that it's biased, how do you get the signal in? Well, through a very large capacitor, right? And so if you have a very large capacitor, this would get shorted, and then these things that don't look like they're in parallel, RG1, RG2, actually turn out to be in parallel. But that's not really what today's about, and you're going to get that in 122. All right, it's just not everybody's at the same level, so I thought to, okay. So again, we have a circuit, and in this case, I think they really just wanted V out over V in generic terms. You didn't have to calculate it. All right. But so the thing is even though I know that this would be minus GMRD here, this is also acting as a load to it as well. It's not like perfectly buffered, right? If I had in between there an op amp, right, I could solve this node, right, and then solve whatever relationship this is, and then just multiply them together. But they're connected by a wire, So I can't really do that. All right. But I am thinking that the output of this is going to be negative, right? So, um, I'm not going to go through the DC part because that wasn't part of this problem. So I'm going to convert this to the small signal model, right? So let's just call it GM1 VGS. Well, so VN equals VGS. Okay. Here, now this is another current source, and it's since the little arrow is pointing out, that's another NMOS. So I'm just going to draw another one, and I'm just going to keep it GM2 because I don't know, it'll definitely have a different value, right? GM2, but now what's VGS here, right? So this is drain 2, gate 2, source 2, right? And so this voltage, to turn this on, it's the voltage between here and here that's important, not between here and ground, right? So it's not VB, right? It would be VB minus VX, because that would be the gate and that would be the source. All right. But over here we have RD2. Ooh. Sorry about that. Oh, it's still doing it. So I can say VN because VN equaled VGS because that source was tied to ground. Okay. So let's try to so I have this coming in the node, and I'm just going to call that ID2. This is coming out of the node. Right. And now, yes, some of this current can be pushed that way, and some of this current can be pushed that way. IRD1, I'm just going to have it go this way. Hopefully I get it right. and I'm going to have it go in the direction. So that would be, so this is in, out, out, plus. So now what to do with this VB? Well, it's not an input or an output. And so, yeah, with experience, I can tell that, well, that's just some constant voltage they're using to turn the transistor on. If it wasn't, then they would tell you to find V out versus VB and V out versus V in, right? So actually, this idea of small signal analysis, what's the derivative of VB if it's a constant? It's 0, right? So this becomes GM2 VX, and there's a minus sign there, right? So what's ID2? Minus GM2 VX. What is ID1? GM1 VN. And I need to redraw this so I can understand it. Oh, sorry, I blanked there for a second. So in this case, right, I'm just defining, this is Vx. I'm saying the current is going that way. And so I should have, what should that current be? Right, Vx divided by RD. Okay. If I know what that is, well, then the current is that. Because remember now, these two aren't equal to each other because we're adding another current source. Okay. So now we're going to have minus Vx GM2 plus 1 over RD equals GM1 V in, V out. Oop, it's Vx. Vx over V out is going to be GM1, GM2 plus 1 over RD negative. Okay. Now, if I just and I got to be honest, I have a hard time making these things neat, right? Because in order to make them neat, you got to do them 10 times so that you don't make any mistake, and then you've got your derivation planned out. But really, if this is 0, right? Let me just redraw this bit, right? Now, even though it's not making a loop, it's splitting up, the current here is the current there, right? And so, like we did in that's just a common source in this configuration, right? It's just common source, but that VB is 0. So actually I get, sorry, GM2 VX And so V out over Vx is just GM2, no, GM2 RD2. I'm sorry, I'm really running out of room here. So now V out over Vn equals GM1, GM2, 1 over RD1 times GM2 RD2, and then you have the minus sign. So it was minus, right? And then one of the questions was, what if this, the drain resistance on 1 goes to infinity? Well, then this drops out, the GM2s cancel out, and you just have minus GM1 RD2. And I think what, like what would be the point of that? I don't know. Is that if this goes to infinity, right? Well, then it's like it's not there. It's so big that it's actually an open circuit, right? And then this transistor being on, right, is just connecting you to this here, right? So, right, so this transistor, when it's just on, it's just a current source, and what's ever leaving and entering the node, it just kind of balances itself out, and ultimately you back to a common source amplifier. Okay. At least that's my interpretation. I know that was a lot of theory. And again, I'm just kind of doing these a little bit off the top of my head. Okay. But did you have any?
What was the final V out V in equation you ended up with? I think it's there.
All right. So what? It should be GM1, GM2, RD1 times.
I think it was GM2 RD2.
Yeah. And then there's nothing there. And there's the minus
and
sign.
Negative.
Now, yeah, I did a loose thing in LTSpice to show that that was true.
So I guess I don't feel like I've heard the derivative thing before, but now seeing this, it's making a little bit more sense.
Okay, yeah.
Can you elaborate on that?
Well, the thing is I forgot I used to say it like that until about 5 minutes before class. So it's like one of these things, you can get so used to doing it, it's like you forget why you were doing it. Okay. And so I know it might sound like I'm repeating myself, but I'd like to do it with the diode. Okay. And that is just N V threshold, so I don't have to write it over. V thermal. All right. So right, clearly nonlinear, right? But you pick a point and you say that you're only, so I'm only going to vary, this is VD, right? A little bit. Well, what's a little? Well, deltas are little, right? And I'll get an output current. Well, if this is little, oh, sorry, somebody's playing the TV. So I have delta ID, right? Now, if I, like I said, if I zoom in on that, really zoom in, it's going to look like a straight line, right? And so what's resistance, right? It's no, whew, right? It's voltage divided by current, right? But it can also be like delta V divided by delta I, and the slope of this line, right, is what? It's delta ID delta VD, but then that means that the resistance RD equals 1 over that slope, right? So I just kind of take it like, take the derivative of the thing, right? And that's what you're doing for small signal analysis. That's why it's called small signal, because we're only varying a little bit, right? So that's one way, but GM is what? Right? To find GM, you're taking the derivative of that, right? And so to find ID, I can take the derivative of that, but of course it depends on whatever VD is to begin with, right? So you are taking a derivative. So if I have a constant voltage source, right, 5 volts, 15, right, well, I'm taking the derivative of everything, really, of any signal source. And what's the derivative of this? 0. It doesn't change, right? So does that help?
Yeah, it helps. I'm just trying to solidify that connection. So it's kind of like we're rewriting the circuit and taking the derivative of everything because it's going to help us find more values. In particular, this resistance, which we relate to GM and all that to find.
Yeah. Here's the thing. We're breaking the problem. These analog problems, we're breaking up into two things. We solve for at DC, where usually you open up every capacitor. Well, yeah, you actually open up every capacitor, right? And that kind of leads to here, is that, let's look at this problem. Let's look at it at DC. Infinite capacitance, infinite capacitance. At DC, right, the impedance of a capacitor is infinite. So in fact, you take it out, it's not there, right? And so I have a voltage supply, and it's tied to ground, but there's no path to ground. So it just seems to me like a trick question. Like, nothing is nothing, okay? There's got to be a loop in there somewhere for current to flow, right? So if there, now, yeah, if it's like, well, those capacitances aren't exactly infinite, and maybe your DC, I mean, nothing is truly DC, right? It's really close to DC. So maybe there's a little bit of connection there, but it's, or that capacitance has a leakage, right? I mean, you have a capacitor, right? But capacitances have an inductance and they have this leakage term. That's like a real capacitor, oops. So, okay, there is a resistance tying these down that, like over time, something would happen. But from an ideal point of view, oh, and depending on a capacitance's parasitic resistance wouldn't be a good design technique, right? So, and yeah, I mean, there was a professor, he would make these, what you might call really complicated circuits, you know, and then call V out, and he'd have it tied to ground, right? Well, people look at all this complicated circuit and like, yeah, well, it's zero, right? Or I've seen like all these complicated circuits, and then somewhere in between, there's a current source and a resistor, right? So there's all this distraction. And they'll ask you, what's the current through the resistor? Well, whatever, it's one branch, it's whatever that is, right? But all these things, devices you've never seen before, right? Doesn't matter. That's a current source and a resistor. That's, or it does, it doesn't even matter what the device is. Ideally, it would push that current through no matter what. Okay. But that's, I don't know. I mean, I did have like a few computer failures between the last, when I taught 122 a long time ago. Like I only had the PDFs. And it looks like it was just some example I've been working on.
Well, thank you. I've been doing the small signal gig and AC analysis, but I guess I didn't quite understand why. And I think that
Oh,
kind of
because
breaks it down.
because it'd be darn near impossible to design. So here's the thing, right? I could put this into LTSpice and it would give me a value. But what R's will work? What currents will work? I don't know, right? So it's just too complicated to do by hand. So you break it up into AC and DC. And here's the thing, and this is more 124, or I don't know where I put it, but so here now you have like this is like the circuits inside an op amp, and we're not even using resistors anymore. All right. And we actually use the GM over ID technique. But the thing is I want to, where's my, so I have this gain, right? Minus GM, and here's some parallel resistances, right? So I have the GM and I know that. But to find this value and this value, I actually have to extract it in LTSpice at a fixed current, right? Then the next stage, same kind of thing. And then when I multiply them together, I should be able to get, what's the total gain? This times this. And which relatively matched, right? But notice that that gain is dV is the derivative of V out. Well, now we're already talking derivatives. But if you're like completely lost right now, well, yeah, I would imagine you would be. But trying to use the saturation equations, ID equals Kn divided by 2, VGS minus VT squared, and all that, right? No, that's what LTSpice is for. Okay. But the thing is that this is what LTSpice does. Actually, you just don't know it. Let's see if I have anything. Okay. So this is a fourth order Butterworth filter, right? And so you run it and you get your classic Bodie plot. What you don't know that it's doing is it'll run a DC analysis, right? And notice here I have these 5 volts and 5 volts and 10 volts, right? And it'll calculate everything at that one DC point. And then it's effectively, once it has that, it just replaces this with a network of like a gain stage and various capacitances or a transfer function, right? And goes from there. Okay. So LTSpice is doing a DC analysis first. And let me see, I had a few. Right. So if I put in 1 volt here, and then say I'm going to simulate a Bodie plot, decade 21. Okay. It will find the DC operating point, the current, find all the resistances, everything. It will open up all these capacitances, but then during the AC plot, then it brings those capacitances back in. And that's what it looks like in frequency. Now, if you take it out long enough, it'll come back down. But in 122, you were in this region where it's flat. And if I bring the frequency up, so in 122, you're in this range here, okay? Where the capacitances are kind of neglected. In 124, you're going to be in this region where you have to take into some capacitances are important. Some you still kind of ignore, okay? So now, yeah, I had wanted to actually start talking about research, but that's, that was some questions that had been cropped up during the week. I think next time I will talk about a research topic. Okay. It's now, yeah, if you just came out of 122, you should be able to follow that conversation, no problem. If you haven't had it, don't be too frightened, but you just have to, problems have to be done, in a two-step process. And even with these transistor circuits, which are nothing but gain stages, because they're not like op-amp circuits, you have to take into account everything at the same time, which does mean some nodal analysis. So if you want to do yourself a favor before 122, really get that nodal analysis down and really understand that those current sources on the transistors can kind of mess you up. And you have to know the difference between the voltage drop across a resistor and the voltage measured between 2 points on a circuit. Okay, but when I learned it, I thought, it was random. Sometimes it's negative, sometimes it's positive. I had no idea until I started thinking, holding an imaginary voltmeter in my hand. And if I'm measuring it across the resistor, I might get one thing, but then if I measure between two different nodes, the magnitude would be the same, but I should get, a different sign. All right, but that's what I have. How's everybody doing?
Good, all right.
Good. Okay. Oh, here, you know what I'll do? There.